enough, I think.
Okay, so my recording has begun. So welcome to Deep Learning Adventures. If you haven't joined us before, we started about a year ago, and I'm happy to have my co-hosts George and Robert here tonight. We have people from all around the US and the world to join us often. So if you're not aware of our group, we have, I'm going to go ahead and share the screen here to show you a little bit about what we're up to. Oh, sorry. Where is it? Sorry, I can't find the screen now. Here. It's not the whiteboard. All right. Give me 1 second. Okay. So let me know if you can see my screen. Yep. Okay. Yep. If you're not familiar with us, here's our meetup group, description of what we do. We've gone over everything to do with deep learning and machine learning, as well as some data visualization and many other things that we like to pursue, as well as some coding exercises. We've gotten, most of our things are recorded on YouTube, and we've got 4 playlists now on YouTube. We've got one that goes with our the Adventures in TensorFlow. That was our first one, was TensorFlow in Practice, the Coursera course. And so we go through every one of those classes in there. We also did some, after that, we did some live coding reviews of some different problems that we attacked in different areas. And then we have a speaker series where we've asked people such as the authors of different courses to talk with us. We've had the some of the people that were the authors of the Kaggle courses come and talk to us, and other people. And we're finishing up now a list of Kaggle mini courses. If you're familiar with the Kaggle platform, they have some really nice mini courses that get you started. And that's our last playlist. We also have a pretty active Slack group. Hopefully George can maybe post the invitation link for anybody who's not joined us. If you're not familiar with us, here's a look at that. Can you guys see the Slack?
Yes.
Okay, I just want to make sure we're switching. So there's what's going on there. And feel free to join us. We've got pretty active things where we talk about coding and different data sets, our events as well as other people's events. And you're welcome to introduce yourself to us there. And we actually talk about things other than deep learning sometimes, as well as very technical discussions. I'm privileged tonight to introduce you to our speakers who are going to give us a presentation. We had a series of maybe 3-4 weeks ago now that we looked at, where Robert Kraig had introduced us to an application he built for tracking bikeshare within the DC area. And we went through the data that's available from Capital Bikeshare. And tonight we're going to complete that discussion with some actual models that hopefully predict when bikes are available and when stations have room for you to return your bike. And I'm not sure what else, but I'm excited to hear, see what it does. And in addition, since then, I believe we have Kathleen, who's going to talk to us about more analysis of the data. And I'm looking forward to that, and an even deeper dive possibly into tracking the bikes and things like that. We'll see more on that. It's pretty neat. So I'm going to turn it over to them for now. And I'm not sure who's going first. Is it Robert or Kathleen? Robert will begin.
Yes, I'll be going first. Can you hear me? I thought I heard a whistle or something in the background.
That was my phone.
Okay, no worries.
So
I'll be going first on introducing the problem, the data set, and provide a little bit of motivation. Then I'll turn it over to Kathleen, who will talk about a problem that she did on part of the data set. She'll introduce some graph theory and go into a network analysis that she did of some of the ridership patterns. and then I will come back into my modeling notebook for TensorFlow. One thing I do want to do is disabuse folks of the notion. Thank you for the intro, David, by the way. But one thing I do want to disabuse folks of is the notion that this subject will be anywhere near completed tonight. I think I'm just starting to scratch the surface, but it's been a fun journey and an excuse to learn more about the inner workings of TensorFlow and think more about these time series modeling problems in general. So, as you know, the topic of today's talk is deep learning day trip, and in particular, we are discussing the Capital Bikeshare dataset. And to step back a little bit, we'll think about the transportation problem in general. And in urban areas in particular, people who wish to transport themselves from one location to another often have many options at their disposal to choose. From private automobiles to buses to metro trains to bicycles to just walking to get where they want to go. And all of these options have there are a number of factors that one will consider when choosing an option, such as how long will it take for me to get where I'm going, how much will it cost me, and that cost, I guess time is part of the cost, but there's also a financial cost involved in the vast majority of transportation decisions. In addition to that, there is the convenience. There may be some thoughts about the weather and other things that may make certain choices less optimal. And there's also just physical and mental well-being. I know that I, as someone who does enjoy bicycle riding, is very often willing to trade a larger travel time for the ability to choose that mode of transportation. But that being said, the urban environment does lead to a lot of, I'm going to share my screen here briefly because let's see, need to get the zoom. Yes. So when we make our decisions are often impacted by others' decisions, and the decision that someone may make may depend on what others have chosen. So the classic example of this is the fact that the private automobile is, of course, the quickest way for most people who own one to get around, unless, of course, everyone else chooses the same thing. I assume you can see this canned picture, just testing to make sure that my screen is sharing.
Yes, we see it.
Okay, great. So yes, the automobile is great for many things, but it turns out that it really doesn't scale very well in an environment where population density exceeds a certain threshold. So metro and buses and public transit are part of that equation, but in many cases, they may not go to where you want them to go. They may not be as flexible time-wise. You may have to wait a while. So there's a bit of a tug of war between the on-demand services that are available at any time versus the large-scale, highly scalable systems that maybe inconvenience your travel a little bit. Bicycles kind of fall into a medium category where as long as you're not going too far, they can be a lot more convenient than public transportation if the transit systems don't go exactly where you want them to go. And they can also be easier to get around in when you're facing high traffic situations like this. Often bicycles can get around jams such as this, and they can use trails or other things. And there's also the physical and mental well-being portion of the equation. So all of this is a long way of saying that in recent years, bicycling has really exploded as a way to get around in an urban environment. bike share systems started about 12 years ago. I think 2007 was the first one somewhere in the world. I don't actually know where, but I think the first ones in the United States were in the later part of that decade, around 2009 or so, or it may have even been 2010 when Capital Bikeshare in DC did start in 2010. So what that does is it offers the bicycle fleet available to people who don't necessarily need to own their own bicycles, and it also extends the bicycle as a means of transportation to those who may only wish to take a one-way trip. Maybe for some reason they are getting a ride back, or the weather's going to turn to something they don't want to ride in. They can take a train back. It offers a lot of one-way options to have a shared system like this. Many people these days use Uber or Lyft services for a similar purpose, but bike share predated the explosion of those services. You also have many electric scooters and other similar mobility options in cities these days. So Capital Bikeshare is the DC version of docked bike share. It was owned and operated by Motivate LLC for the longest time, and they were a couple years ago. The bike share portion was bought out by the Lyft company, which is of course more famous for their other types of ride-sharing activities. So I'll go to the Capital Bikeshare website just to give you an overview of. Let's see. We have. This is the main website. Just a bit of introduction to the different types of memberships that one can do. We're not going to go into the details here, but just showing you how you can get around your city, in this case DC. What they also provide is a map that shows real-time availability of all the fleet, the bicycles and docks in the fleet. So a couple things about this visualization. You will see black circles with bikes on them in some places, like over here, there's a few of them. And you'll also see green dots, yellow dots, and red dots. And the black circles are a new phenomenon within the DC system. These are actually dockless electric bicycles that are part of the system. I mentioned them to describe what is on this map, but for the purposes of the analysis that I'll be showing, I'll be focusing exclusively on the docked system. The difference is that the docked systems operate at fixed location stations, which is where all these green, yellow, and red dots are. And at each one of those stations, there's a fixed number of parking places for bicycles. Riders are financially incentivized to drop electric bikes at these docks, and they must drop the non-electric versions, which are still the majority of the fleet, at these fixed docking locations. But there are now electric options available that you can use dockless to expand the reach of the system. So you'll see, if you're familiar at all with the DC Metro system, but not with the bike share system, these are far more ubiquitous than the heavy rail subway stations. There are maybe, 80 metro stations in the greater DC region, which extend all the way out to distant suburbs in some places. But the bike share system right here, I believe as of now, has 600 plus active docks. Many places, if you go to the center of town near downtown, you get an option every couple of blocks. If you go further out, they're a little bit less ubiquitous. So the other thing I wanted to point out is why some of the dots were green, yellow, and red, because that will motivate our discussion for the evening. The green ones mean that there are more than a certain number of bicycles on the dock. That I think that number depends on the capacity of the dock, but it means that there's more than 10% of the docks are full. You have a confidence that if you show up at the dock in 5 minutes, you'll get a bike. The yellow ones have maybe one or two bikes. The red ones are completely empty at the moment. As you zoom in, you actually see that the visualization gets, I think it's actually a little bit harder to see the colors here sometimes. The other thing that can be unfortunate about this choice of visualization is that it's not just the availability of bicycles that's important here. We're also interested as potential consumers in the availability of docks. Because remember, if we have a mechanical bike, we must find a docking station for it. And if we have an electric bike, we're financially incentivized to return it to a docking station as well. So that is a little bit tougher to see here, but you would determine it just based on the fill factor of these green lines. I believe if the green extends through the entire width of it, actually I don't see any here that are obviously different from one another.
So Robert, if you bring a bike to a full dock, you can't leave it?
That's correct. If it's a mechanical bike, not an electric one, you have to find an open dock at which to park it. And that leads to a number of problems and actually leads me directly into the next point that I wanted to make, which is that ridership patterns and commuting patterns tend to make certain docks very popular at certain times of day and other docks less popular. And you will often get situations where the flow or the net inflow, the net number of bikes in minus number of bikes out is unbalanced at a particular time of day. So in the last version of this talk, I think we did describe a couple of things here, but one of the visualizations that was shared was a look like this. And here what we're looking at is all the docks that we were looking at previously, but the colors now mean something a little bit different. The green docks, this is data that have been aggregated over 8 a.m. from over the hour between 8 a.m. and 9 a.m. over many days, I think weekdays only, if I recall correctly. But you're looking at the net inflow of bicycles, and the inflow is green, meaning that a station that is green tends to accumulate bicycles over the 8 a.m. hour. A station that is red tends to lose bicycles over the 8 a.m. hour. And these patterns are not especially surprising if you're familiar with commuting patterns and job office locations in the DC area. You find that the downtown central business district, which has a lot more people employed there during the day than living there at night, is where you get these really large green circles. So during the morning rush, which we're plotting here, you see that there are a lot of stations that are just accumulating bikes rapidly. There are a number of strategies that the operators of the system have to deal with this situation. One strategy which works pretty well for the morning rush downtown, because the bicycles are going to all pretty close locations, is that they've decided to set up corrals where instead of just having the physical stations where you park it without anybody there, some of these stations are actually attended by Capital Bikeshare or Motivate employees who can check the bike in for you, and you don't have to find an open dock, official dock. You can just turn it in there and be guaranteed a parking spot. To my knowledge, there's no similar system used during the evening rush. The locations would be a little bit too spread out to accommodate that. I don't know if there are corrals in the evening for disbursement downtown to collect bicycles, because in the weekday evenings, you get the exact opposite problem. Bicycles tend to be downtown DC tends to empty out very quickly, and the bicycles tend to accumulate in these more outlying areas. A complicating factor that makes the effect a little bit stronger in the morning than it is in the evening is the terrain of the city, and the fact that some people are lazy and like to ride downhill but not uphill. So the central business district is quite flat and at a low-lying elevation. If you recall, DC back in the 1790s was originally built on a swamp, which the National Mall is extremely low-lying. But the entire central business district is fairly low elevation. And then you get to other highly residential areas up here, with places like Columbia Heights, and the name says it all there. It's not a mountainous city, but it's a couple hundred feet elevation above the center of town. So somebody who may have been inclined to take an easy bike ride downtown during a cool summer morning may be much less inclined to do so at 5 p.m. when it's 90 degrees going uphill. All of this is a way to motivate the problem that I am posing here, which is to say, how might we optimize operations? What we really want to do is be able to predict ridership. And there's several different types of user stories that you can imagine developing for customer or user cases of interest. You can think of a government planner might want to know why or which station locations are popular now and be able to predict where more capacity is needed for future station installations. The operations team actively trying to cope with rebalancing the system during the day. I did not mention, but they do have downtown as part of this corral system in the mornings. There'll often be vans operated by Capital Bikeshare, which attempts to alleviate some of the surplus, moving the excess bicycles to the especially popular stations that aren't too difficult to drive them out to in a van. So some of these stations out here along U Street or in Capitol Hill especially, you might be getting deliveries during the morning that replenish the docks that are rapidly decreasing when people are leaving their homes to travel to the central business district. So a third user story is one just of the consumer themselves. If you are a rider of Capital Bikeshare and you want to know if you're going to be able to leave your home and get a bicycle, maybe you want to know 10 minutes from now, is that bike that's on the dock here at Mount Vernon Square, is it still going to be there? Are the 3 bikes that are here at the let's go up to Columbia Heights, extremely residential areas over here that have very high volumes. You might want to be able to predict, are the bikes available? And that's actually my own introduction to this data set as a consumer, but one who lived in the less busy parts of Arlington over here for several years. I typically did not have too much of a problem with imbalanced stations leading to unavailabilities when I wanted to ride at usual patterns. But I would often find myself downtown at a certain hour in the evening and would want to know, where can I go to get a bike? Now, there are a number of apps available for that. Capital Bikeshare, what's the name of it? Spot Cycle is I don't know if it's worldwide, but I think it's nationwide at least, where you can get data on real-time availability visualized on your smartphone from a number of these systems. At the last meetup, I presented an app that I had developed to take the same idea, but to apply it to a flip phone, because at the time I was a Capital Bikeshare rider, but had not yet decided that I needed a smartphone in my life. So I decided to try to take the data, which was available on Capital Bikeshare's real-time feed, and build myself an app that I could interface with on my flip phone, where I faced 2 challenges in doing so that the smartphone did not. And namely, it was, 1, I didn't have location services on the phone, so I had to figure out how to query my own current location. And 2, I had to figure out how to communicate the information without visualization. But we described that in detail at the February version of this meetup. So if you're interested in that, I highly encourage you to check out that link, which I'm sure has already been posted in the chat. That's just an introduction to my story. I think there are a number of interesting differences between these user stories, which I'll go into a bit in my own portion. But I want to go now into the data sources which are available for the data sources that I utilize to start answering these questions. Capital Bikeshare sources downloadable files of its trip data, and you get a number of rows. Each row has basically a date and time, a location, bike number, member type, and you get to know where somebody took a bike, when somebody took a bike, and where they deposited it. The electric bike rides have been anonymized to a greater extent. They're all anonymized. You don't get user information, but you do get station information. But to protect privacy, the electric bikes, which are being dropped at actual lat longs off the grid, are encoded somehow to obscure that. Anyway, so the data, I think we have a bit of a visualization of what the data frame after significant cleaning looks like. We have basically time at which it was taken, station number, ID number, and name, time at which it was returned, station number and name, duration of ride, and whether it was one of two user types in the system. Some other data sources that are available, but I will not be using, is the Capital Bikeshare tracker. This one says something went wrong here, but I think the graphs and reports section has a number of information. What you can get from the Capital Bikeshare official site does not include information about when stations were empty and or full. If you are interested in that information, which could be very useful for developing predictive models and interpreting past data, you can find that, which has all been collected here through the labor mostly of one individual, I believe, Daniel Golke, who I met at a DC area meetup focused on transportation data sets several years back. He put together this information, which could be very useful if this is the problem you're looking at. I may return to this data, but I won't be touching it tonight. Another data source that I used, I did assume that weather would be an important predictor of usage. People are much more likely to ride when it's weather is calm and 60 or 70 degrees conditions than it is when there's precipitation, extremely high winds, snow, etc. We get all types of weather here in DC. So I got this weather information from this API. You can learn a lot more about that from the last talk or from visiting my other notebooks on GitHub. Speaking of those, I think here's my repo that contains all the information that I've worked on this project. What was presented last time was the data acquisition pipeline, which has been turned into a script at Cavi update raw data. So you can rerun this at various intervals to update and get the recent data. And I did a lot of data cleaning, exploratory data analysis, just to prepare it for the machine learning tasks that I wanted to pursue in Notebook 2. So with that in mind, I did want to mention, I thought it would be a little bit remiss in not mentioning it tonight because it's been in the local news here in DC. The safety record of the DC bike share system is actually quite excellent. You get these interesting shock value headlines. US bike shares have killed a shocking number of people. And it turns out that according to this, which was written in 2014, no one has died. This is August 2014. And then you'll find some other studies here where people try to look at why are the death rates of people riding bike share so much lower than those of biking more generally. And there's a number of interesting hypotheses for that. I won't go into those, but we did recently, unfortunately, very tragically, there have been deaths since then. I think the first one in the U.S. was Divvy in Chicago, their bike share system, had one in somewhere around 2015 or 16, which was the first one ever. And there have been several across the US since then. I think it's still just a handful. I think the first one in DC was several years ago now. But there was actually one just the other day, Friday evening. A young man was struck on Massachusetts Avenue and passed away as a result of the incident. There were 5 vehicles involved. It definitely seemed it was a bit of a mess, and just thought that with that in the news, wanted to make sure that you all were aware of it, and just wanted to bring that up to just give us an excuse to take a few seconds to really think about how our actions affect others. From the stories that I read on this particular incident, this young man was on the bicycle was almost certainly not in any way culpable in his own death. Just a matter of being in the wrong place at the wrong time when a driver of a motor vehicle likely did something stupid. But that's speculation, just based on the facts of the case. I think, though, that it's always worth pondering these types of things, and would ask that we just take a few seconds here to pause before we move on into the next portion where Kathleen will be discussing her data analysis. I want to just take a few seconds of silence to think about how our actions impact others and how we can live in a way that reduces our negative impacts on other individuals in light of the traffic deaths that occur 40,000-ish in the US every year. So we'll take a 30 seconds just for reflection. All right, thank you all. We'll return to the topic of tonight's meetup. I kind of raced through material that was covered over the last session, so wanted to ask. I haven't seen any questions, and I'm not seeing the chat, so let me know if there are any questions on the material that we've covered before we move on.
There was a question if there would have been differences in ridership patterns pre and post COVID. Someone asked that in the chat.
Yeah, and I actually thought about sharing that as part of the intro. There are, I think the best way to answer that is probably with this figure, which I don't know if it's labeled. Yeah, here it is. So what we're looking at here requires a bit of an explanation. Each color on this figure is 1 full year's worth of data. And the x-axis is the total number of hours since the very first Capital Bikeshare ride was taken back in 2010, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20 is this one. So you can clearly see that during the peak when most activity was shut down, there's a significant drop versus the spring of any other year. And even since then, there's been significantly lower ridership than there was before. This is system-wide. I'm sure there are effects that vary from station to station, but this is kind of an overview. You can see that it had started to decline a little bit before this year, 2018 into 19. I don't think this is so much the demand decreasing so much as there's just been a lot of competition. The last couple of years, there's seen a lot of alternatives like scooters and more people using services like Uber. So I think that may be more to explain for this, but the pandemic is clearly visible for sure.
And when you go into DC, it's like a ghost town. It's eerie to be there when there's typically was a lot of traffic. Nobody's there, so I'm surprised it's even as high as it is.
Well, there's still a lot of people that live all around town, many of them without cars and are still going some places. So it is an interesting observation, though, and it does beg the question of what will happen on the other end of the pandemic.
Hmm.
So with that, I'll ask with that, after that long intro, we'll ask Kathleen to share what she's discovered about this interesting data set.
Boy, it's been so long, I forget how to start a presentation. It's not in view.
So down at the bottom, there's a little, looks like a slide up. It's right to the left of there. That little, right before you get to where it looks like there's a book open. Yeah, that one.
Yeah, it's partially hidden from here. Okay. First off, a million thanks to Robert for, well, mostly for cleaning this data, but for inviting me to talk about it and to play around with it. I saw Robert's presentation and just thought, wow, this is nice, clean data. He did a tremendous amount of work on it. It just looks like network analysis to me, or that it was ripe for network analysis. I've done a fair amount of that, but it's been a few years, so it was fun to get back into it. And so I'll start by just briefly describing, give you a little intro to network analysis. So the vocabulary, a node or a vertex is just an object of interest in a system. And an edge or a link is just some way, a connection between two of those objects, two nodes, this signifying some kind of relationship, any kind of relationship you're interested in. And then a network or a graph, or a set of nodes and edges, it could be directed where the connection is from one node to another, like this person likes that person, or this bike is going to that station, or just saying that these things are connected, they're friends, or they're near each other, or something else. So each of these, the node, the edge, or the network can have associated attributes. And then network analysis is a set of techniques or methods that try to characterize the relationships and what that system, what's going on with that system. And there's the visualization aspect of the analysis. So I just find the network diagrams fascinating, and I came for the pictures and stayed for the numbers, and the numbers are the metrics. They can be on the entire graph, they can be on individual nodes, and some of them could be on edges also. And they're really very interesting. Some of them are straightforward. Some of them are like telling you something you wouldn't have imagined. And then graph theory is the mathematical foundation behind the network analysis. There's a lot of development in network analysis and social network analysis by sociologists over the last century. But then there's, graph theory, graph analysis is an ongoing mathematical discipline. So, so in the social network analysis, it studies of friendship networks, communities in general, nefarious groups. I worked a little bit in analyzing terror networks. And then, of course, in recent years, just a plethora of the online social media is just a tremendous source of linked data. You can use network analysis to study information flow through a system, to study traffic, to study, it's used in epidemiology. I mean, our recent experience, what we've been living through, how does this disease travel from group to group, biological systems. There's a lot of development in biologists, I think cell biology. I'm not familiar with it at all, but I know they use link analysis and network analysis. So this is just a picture, I mean, of a network and the kind of thing that I look at it and I just really want to play around with it. You'll see that the links, the edges here are all the same size, but edges don't have to be. They could demonstrate how strong a connection is by their width or their color. And the other attributes can be represented by size and shape of color and shape of a node, and different metrics like importance could be measured. Some definition of importance, which I'll talk about, could be measured by size. So that gives you a way of seeing a really complex set of information using our visual cortex, which is so powerful. So, so I have focused on Python in the last few years. And so I now do network analysis with NetworkX. I find it to be a really nice package, very easy to work with. It reads and writes various graph formats. GML is a format that it's a list of lists. So you can have the network would be a list, and then the nodes, you'd have a list of nodes, and you'd have a list of edges. GraphML is an XML format that I'm more familiar with, and it shows up if you open a GraphML file in Sublime. The coloring is in the indenting makes it really easy to see what's going on in that network, the shape of it, sort of. So you can create NetworkX. You can create graphs from lists of edges, or they now have to and from Panda data frames. You can easily add graph attributes to your graph, to nodes or to edges after you've already created the graph. They've got nice documentation too, and a tutorial. It produces a ton of metrics. It's really very rich that way. Visualization is not a big focus of NetworkX. I just picked up this, quote today. It says, proper graph visualization is hard, and we highly recommend that people visualize their graph with tools dedicated to that task. And they recommend Cytoscape, which I'd never heard of until recently, Gephi, and GraphViz. I have used Gephi in the past and saw this. If you see down in the corner, this guy, Peter Lawson at Johns Hopkins University, has a page on data visualization in general, and a section on network visualization. He recommends Gephi. It's a standalone product, so it's not, it's like a dashboard that you import your network data and then work through the dashboard to see what's going on. I'll show you a little bit of that in the end if there's time. And so he says it's a leading visualization and exploration software for all kinds of networks. Accepts many formats, and I have not worked with this GEXF, but it's a format for handling network dynamics. So time series of networks, which is really an interesting concept. So you can do it either continuous time where the time is in floats, or timestamps. So it would be a stepping through a time-stamped set of data, and it enables various parameterized layouts. So a layout is how that you represent the nodes on a flat image, and you can do that in a number of ways. And you in Gephi you can reset your parameters to do that as you wish. iGraph looks really interesting, and that could be used programmatically. I'm anxious to start playing with that, and PyViz as well. Evidently, this Viz.js is a popular library, and PyViz is a wrapper for that. And then, let me keep my fingers off the graphs there. Julia graphs. Somebody, a woman in our group mentioned that, and it's also it's a set of Julia packages for graphs, including visualization with those packages, and that looks like it could be really interesting and powerful. So they're worth looking into. So the network metrics. So that was the visualization, and then the other magic of network analysis is all of these metrics that you can produce with your from your graph. So there are a bunch of centrality metrics. Degree is the simplest or most straightforward to imagine. It's just it's a popularity, the number of nodes that are connected. So with a node that you're focusing on, the number of nodes that are connected to it, whether it's directed in or directed out, or both, depending on how you want to, your conception of the network. Then there are other centrality metrics that consider how popular or how important the nodes you're connected to are. So if you're connected, if you've got a high degree, but you're really connected to a bunch of nodes that are not considered really important, then you wind up with these eigenvector cats and PageRank. Take that into consideration. Closeness is the so a path through a network is stepping through a set of connected nodes, and there are shortest paths between nodes. And then if you look at the mean shortest path from a node to all the other nodes, that's its closeness centrality. The one I find most interesting is between this centrality. I call it a renaissanceness metric, because it measures that it might be a node that does not look important based on the other metrics, and yet it's on the path between otherwise unconnected nodes. And so it's really important, because if it's cut, then you have cut the connections between the sub clusters of the network. And that could be something you really want to do if it's a disease and you want to stop it, and that's why we're all staying at home. Or you've got a nefarious group and you want to make sure that they're not sharing information so easily. Or it could be something where you've got a network. I was working on a community of practice for computer science teachers, and we wanted them all to share with each other. So we were looking for the people that had high betweenness centrality, because those were the people we really wanted to encourage and foster and promote, because they were connecting groups of people that otherwise would just not be able to share their their information with each other. So then edge metrics, I'm pretty sure that it's just, it's some measure on the connection between the two endpoints. So it has to do with what that relationship is. So if it's like, if it's sharing money, it could be how much money is it sharing, so that metric, the weight would consider that. If it's, yeah. And then there are metrics that are on the entire graph. So the density of the graph is like the actual number of edges versus the all possible number of edges for a graph of the size that is. So that's a really important. You can imagine if a network has just a lot of connections, it's a dense network, there's a lot going on, or else if it's not, then that's something that would be really interesting and important to understand about your network overall. The number of specialized groups of nodes. So there are cliques, that would be a subset in the network where every node in that subset is connected to every other node. That's a clique. A k-plex is like a clique, but you don't need to have every single node connected. K of them might not be. And a k-core is, yeah, I'm forgetting what that is right now, but it's a kind of the mirror image of a k-plex. So it's a partially connected subset. And then modularity is really an interesting concept, an interesting metric. So an assortative graph is one where you have some attribute to a node, say which school you went to, and a graph with that's assortative would have people that are connected. You'd see more people connected based on that characteristic than if people were just randomly connected in the whole network. And modularity is a measure of assortativity. And then for graph metrics, there's a lot of them, like the average degree, the average between a centrality, and that sort of thing. So there are more than node and graph metrics than I cover here, but that gives you a flavor for how much how rich that is. So, excuse me, network analysis and pedals to the metal. So Robert's February presentation, as I mentioned on the Capital Bikeshare data set, I just saw that and thought of networks. You've got, they're all this beautiful, clean data with links in between them, and attributes on them. And it's like over an extended period of time. I mean, I just needed to do an analysis of that. Now the problem is, does my analysis make any sense? Does it help anything? Does it shed any light on anything? But and that would be interesting to hear your take on this. So my goal was just to do an exploratory analysis, data analysis, producing a bunch of metrics, some of which might be useful, that I thought might serve as features. So it was like coming up with a trove of features to be used in this deep learning model. And my strategy was to produce networks at different time resolutions. So I looked at year, quarter, month, week. I haven't done day yet, but I plan to do that. But thinking about listening to Robert describe it today, an hourly network production might be even most relevant, but that would be easy to do, just given what I've done so far. So you produce all these networks, produce various metrics for each of the networks, and also for the nodes, and then treat them as a time series for each time period. So you take the on a just say the modularity, for instance, you take that on each of these networks and then see if that changes over time. Does it, well, you know, if it's relevant in the way it changes over time. And you look for patterns and outliers and something like, and then visualize the outlier networks to help understand the anomaly, the extraordinary metrics. It would be, well, with that GEXF, it might be possible to actually examine the visualization to visualize the networks over time. But my thinking before seeing that was to examine the time series, the metrics, and then use the visualization to confirm or illuminate that or do something. So this this is something I sent Robert quite a few weeks ago. It shows the network for I forget a certain time period, a few weeks or something, and just how they're this will you see in a second, but I wanted to point out here that this node here or this one, they would have high betweenness, this one in particular, high betweenness centrality. Because if this node were not here, then these are two separate clusters, not interacting. This one, 31603 is, it's not on there. This one here is 5th and K Street, and this one, 623, is the Columbus Circle, Union Circle. So you can see this has got a high node degree. It's like the central part of it, of this set of stations. So the status so far of what I've been doing, I've developed the Python code that creates all the graphs and the metrics for the periods. Right now I'm covering year, quarter, months, and weeks, and collecting that all into a CSV file that could go into a data frame, and I could just analyze it from there. And it's with any era for small enough from Robert's CABI 7 database, and it examines, and I've examined some of the graphs in Gephi, refamiliarize myself with the workings of Gephi. And what I'd like to do, if life stood still, is loop through all the reasonably sized subset for an input era, or move it to the cloud so it could handle more, and crank out all the graphs and metrics and add the period day. And just as I said before, I'd add hour, and do the time series analysis of the metrics, and then visualize the graph using geolocated layout rather than the spring force layout that I used. I want to show you, let's see, this is Gephi, and this is one of the graphs I produced, and just to show you what the layouts can look like. So
Kathleen, if we're still seeing your PowerPoint.
Are you? Okay.
You might have to share a different window, maybe.
So do I stop sharing and then reshare?
You might have to stop sharing screen and then reshare the other.
Yeah. Okay. Thank you for letting me know.
While you're doing that, Kathleen, I had a quick question. The nodes that were always the stations, is that correct?
Yes.
Okay.
Okay, let's see if I can.
Those are the ID numbers code for the stations. If you've dug into the data set as much as I have, you'll be a little bit familiar with the numbering code. Actually, it turns out that the third digit of each of those tells you what ward it's located in DC.
Yeah, so, I mean, yeah, Robert was suggesting from the beginning, it would be interesting to pull, to, the lat long is contained in one of, or the attributes, or some of the attributes. So that's available to study. So this is one layout. This is another one. And you can see you can, so this is Force Atlas. Actually, the other one also, their repulsion, treat the layout, the nodes like the edges like springs, and so connected nodes pull to each other, and non-connected nodes repulse each other. And let's see if I can. So this doesn't tell you very much because I'm not giving you much explanation, but there's just a lot of analysis you can do, or a lot of tricks you can do with this. I compute the metrics already, but you can also compute other metrics here, and then you can size the nodes or color the nodes based on the metrics that you computed. Right now, I've got them colored by region ID, but you can do other things with it. And it's a pretty rich tool. It doesn't have the look and feel that we're used to in newer things. And there are some, so I'm thinking that iGraph, was it iGraph with the other network tool, the visualization, I think might be, yeah, this iGraph might be have a better look to it, but I don't know that it would be as powerful as Gephi, because it's been around and it's just really got a lot going in it. So I'd be interested. So you can see I did it kind of like, this just intrigues me. It was a nice data set, which is really hard to find. You either have to do all the work that Robert did, or it's not rich. There's just not a lot of content. So we were trying for this community of practice for teachers. We're trying to find, who's interacting with whom, but there really wasn't a whole lot of interaction. So there just wasn't a lot to analyze. So this was really rich. But would it be useful? The concept of just coming up with a bag of features and seeing if that exploratory, and see if that makes sense, could be useful in some kind of deep learning model, is something that I'd be interested in hearing what people think, ideas.
Kathleen, there was a follow-up in the chat on the, I guess the edges between nodes. What do they mean here?
Okay, so I dropped any, so that's a ride, and
so that's the start and end points?
Yes, I dropped any rides that started and stopped at the same station. Okay. And then grouped the rides together within a time period that I was studying, between two stations as two nodes, and that was its weight, and then used a minimum weight that would have been, I based it on like a certain percentage of the days there, so 0.15 per day, and then it had to have at least that many rides to show up in this. And those are all parameters that can be played with if they're worthwhile. Otherwise, there's just too many to deal with in a visualization sense. So I'm just curious about any feedback or any ideas on it. And if not, then Robert has got a lot to show us, a lot more to show us.
I'll give you feedback. I think this is really cool. We haven't done much with graphs, and this is, you're right, this is just a beautiful set of data to do something like that with. Thanks for showing us.
The concepts, I mean, whether it's a nice example of things, but the idea of network analysis in deep learning, I can imagine other situations where it's lends itself more to actually doing something useful. But looking at this out on an hourly basis, I think could be interesting to the source and sink of those bikes. So anyway.
So one thing about it that really interests me is the concept of using it to explore either feature generation for a prediction model or visualization of features that have been generated in other ways to kind of confirmation or just look at it. One thing that could be really useful for a predictive model is to develop some kind of low dimensional representation of the stations themselves, almost like a word embedding is relatively low dimensional representation of a word, much lower than the tokenization where each station is treated as a separate entity. I think the same concept could lead to some interesting analysis here, and is definitely one direction that I want to explore taking this project that I haven't done yet. So really,
yeah, doing a like a multi-resolution analysis of it, where you don't consider you can clump stations in a location in a few blocks together might be interesting.
Right.
So
anyway, I will share my screen and return to my modeling notebook. And we'll skip the setup part. So what I'm attempting to do is explore the problem of forecasting for bike share ridership. So I'm going to start by digging the data out from the same SQL tables that Kathleen had been interfacing from. We have the only data that I'll be considering here are the ridership counts, the bicycle ridership counts, the dock parking counts, which are the inverse of that, and the weather data, which will be an important predictor. And also just gathering some information about the stations here. Pre-processing and feature engineering. So this is an interesting problem because you've got features from a variety of domains. And so here I'll start with the weather. I ended up cutting down the weather features to only 6 of the original features for simplicity. The 6 that I thought would be the most relevant: temperature, dew point, wind speed, the x is east-west, wind speed north-south, precipitation, and snow depth. The described function gives you a little bit of information about each of these features, their distributions. A pair plot in Seaborn is a nice way to visualize these. Temperature and dew point clearly correlate with each other. The other ones are a little bit less so. The wind speed, you can see some artifacts about the way the data were measured. And the precip and snow depth, these visualizations are kind of belying the fact that the data in these fields are extremely concentrated on the 0 column. There are some other points here and there, but for the vast majority of the data are actually right here at 0 for those. So imbalanced features there. So the two most strongly skewed features, I decided to just take a log transform of them to make them a little bit more symmetric. You still end up with skew, and it doesn't change the appearance of these distributions too much, but it does make them a lot easier for the neural networks and other models that we're dealing with to work with. I decided not to go any further transforming them than that. You can see what, I guess the C1 feature here still really doesn't show much. You just see that it's highly concentrated in the zero column for both of these, especially snow depth. So the ridership data are from a different source than the weather, and this is a really interesting question. I'm not going to get into it too much here, but when considering a model, you really want to think about what the model might be used for. And since this is really just a personal project at this point, I can do whatever I want with it. But it's interesting to think about how the different user stories that we talked about earlier might lead to different desired choices for such a model. If you are an operations team moving lots of bikes from one place to another, or maybe doing planning about station locations, you may be looking at more aggregated data. The numbers in general are bigger, and rather than looking at individual station level data, you'll have something which is a little bit more continuous. The central limit theorem applies to bike ridership data as well as it does to anything else. And when you have larger counts in an integer variable that is measured in counts, starts to look more and more like a normal distribution as you start getting larger and larger counts and adding counts from different places. However, if you are the individual user, you might be more interested in answering the question, well, if there's 2 bikes on this dock right now, what is the probability that there's two bikes still there in 10 minutes? Or what is the probability that there's at least 1 bike still there in 10 minutes? What is the probability that they're all gone in 10 minutes? So at that point, you might be interested in more of a Poisson model. So I looked into the Poisson distribution, which is actually one of the loss functions available in TensorFlow. And I ended up not implementing it, and I actually I wasn't convinced that it was being implemented correctly. But just thought I should talk about that difference of problem, because when you get to the individual user, where you're talking about counts that are very small, it starts to resemble less of a regression problem and more of a classification problem. And my expectation before going into investigation of the Poisson loss method was that it would essentially treat the loss sort of like the cross entropy function categorically does, but with a different hypothesis space that's based on counts instead. I could formulate the problem mathematically reasonably well, but then looking at the code that was implementing it, wasn't quite sure what was going on. So if anyone has used that loss function in TensorFlow, I'd be really interested to hear your experiences, because I'd like to be able to apply that methodology to this work in the future. Moving on to other features that we should construct when considering prediction for this data set. The other thing I really should mention here and give credit to is this tutorial here at TensorFlow. I think I put it at the top of my notebook, but then skipped over it here. This is a how-to of time series forecasting that TensorFlow has shared at this link here that I'll drop in the chat. If I can find the chat from this window. Maybe I'll do that at the end of the meetup.
I can post it, Robert.
Okay, thank you, David. So it's a tutorial basically on time series forecasting. They use is it the Madrid weather set that we did before? I don't remember. It's a weather data set. So they are predicting very much a continuous set of variables, and you're looking at things like pressure and temperature. but a lot of the same methods that they use will become very useful for the bike-share modeling as well. So one of the ideas that I borrowed from them is the date and time feature engineering. And the idea here is that you may expect that you have a certain seasonality in your data set. Why not allow your model to be able to discover this seasonality more easily by simply encoding it as a feature? So we expect to have some kind of daily diurnal seasonality. Patterns will repeat over 24 hours. Patterns will repeat over the course of a year, and patterns will repeat over the course of a week. So what the tutorial does, and I replicated here, was basically computing sinusoidal functions that you can use to represent the portions of a day, a week, or a year that indicate what your current day, week, and year are at any given time. So this is what the features may look like. The time of day signal, you just give it a sine component and a cosine component, and you can represent, here we represent midnight as the angle which has a cosine of 1, and noon is the angle with the cosine of -1. And likewise, we do something similar for the week, where it's Sunday at midnight that is the starting point, and comes back around to Sunday at midnight with 2 sinusoids there. And here we're looking at something similar with the year, where January 1st is now the point where the cosine is 1. And then they also, and here we got to see the same visualization of total rides we saw earlier, but I'll skip that this time. There is an FFT code that is interesting for analyzing this data. So at this point, you can take the fast Fourier transform, which is a concept in signal processing that you may be familiar with. Otherwise, you can find resources on that pretty much everywhere. And this will give you a hint as to which components are the most relevant in your data set. As you can see, there are spikes in a handful of places here that indicate where you get some kind of constructive interference in these sine waves. So the most prominent one, not surprisingly, is the daily frequency. The pattern that tends to diminish usage at night and increase usage during the day is a very strong one throughout the data set. There's also a yearly cycle, which is based not only on holidays and other activities, but here probably primarily based on the weather. And you actually, it's very difficult to see the weekly seasonality here. It's almost completely absorbed by what's going on in the daily seasonality. But I did a little bit more analysis here, decided to, rather than sampling once an hour, sample once a day and see if the weekly seasonality is a little bit more easy to see there. And after a few lines of code here, you can see that it does stand out when you do the sampling over 24 hours instead. At that point, of course, you won't see the 1 over day anymore because it's the Nyquist frequency is half that. So just an interesting way to look at the data, and it does confirm that we did not use the sine waves here. This just confirms the fact that our data set is very strongly got these 3 components. So it confirms our choices. For a time series model, data splitting is an extremely important consideration. We discussed this a little bit when we covered the time series units in Lawrence Moroney's TensorFlow in Practice series. But to recap for those of you who weren't with us at that point, it's very important to split the data sequentially. Train, validation, test. Your validation period should be after your training period. Your testing period should be after the validation period. Note that this differs from many data sets where you might want to randomly split data amongst your samples. You'll do some kind of cross-validation and just select different random samples of your data. But when your data are a time series and you expect to encounter them in a given order, it can be extremely misleading and give you unjustifiably optimistic results if you choose that methodology for choosing a train val and test set. You'll encounter situations with where leakage from future measurements will impact your prediction of the current moment, and you'll also have really no idea how much your model might be susceptible to drift in the real world. So with that in mind, another consideration for time series is that when you have seasonality, it's useful to make sure that you're not biasing your train validation and test sets too much. So for instance, in our case here, we have a yearly seasonality. We don't want our validation set to be 18 months and our test set to be a different 18 months, where the validation set might contain a lot of summer, a preponderance of summer months, and the test set is biased toward the winter months. So we want to choose an integer number of, ideally every one of these things. We don't really get the option of choosing an integer number of weeks and an integer number of years with a data set that's only 10 years long. So I chose to keep the years integer, and the weekday bias is going to be an extremely small fraction of that anyway. So not a big deal. The pandemic that we mentioned earlier, of course, has affected ridership significantly, has introduced drift all over. So if we want to be able to measure on data that maybe give our model a little bit of an easier task to start, we may want to consider a test set that doesn't include the pandemic. So I actually decided at this point, well, I'll look at two different versions of the test set. I'll use 2019 as a test set for one possibility, but I'll also use 2020 as a test set just to see how does that work as well. This being said, the notebook at this point below this cell, I think everything is 2019. So I have yet to really explore how the model gets broken by 2020. There also, I didn't have any idea going in exactly what kind of lags would be most helpful for training. So I'm considering starting training either January 2012 or 2013. So this combination leads to 4 possible data sets splits that we could generate here. The rest of this notebook will be based on this first split, which I'm calling 2-7, just the bound last digits of the training years, 12 to 17. The next lines of code here all create a number of Boolean functions and slice objects in Python that allow for easy access to any one of these splits. But I'm really considering everything other than split 27 to be an interesting after-the-fact analysis that I have yet to get to. At this point, we will use some of the analysis we did before on the weather and do some scaling of the weather features. A lot of these things, the normally distributed features, temperature, dew point, wind speed, those ones we will scale down to 0, 1. The precipitation and snow depth, we will, I think I also normalized those ones, the already log transformed versions of those. The details here, I'm going to skip over a little bit. After all these transformations, these are the distributions of the weather features. Temperature, dew point, wind speed are still pretty well distributed. Even after the precipitation, I think even after a log transform on each of these, it's after a log transform and standardization, it still looks very much skewed, with some values having z-scores well above 10, or z-values well above 10. Didn't decide to do any more about that. They're pretty rare in the data set. And again, not too concerned about normalizing. So remember, there's 3 different types of features. The weather we worried about. The date time features, those sinusoids, they're already inherently normalized. They don't have to be normalized exactly to a standard deviation of 1. Just want to get them in the ballpark. The other ones, the ridership features, for now, I have left those as counts. So they're actually on a different scale than the other ones, which will hurt our model as far as training time, but will probably not have a great impact on the actual optimum that it steers towards. That's my thought anyway. That's something further to investigate again that I haven't done yet. So this last section is just generating the full data frame. There's a variety of versions of that too, depending on what we're predicting here. I have a variety of acronyms here at the end: TWA, TWS, CWA. No, I guess the C's are over here, each of which represents different ways of representing the data, different modeling tasks. The one I'll be focusing on the most here is this first one, TWAI, which basically means that we're looking at the time. We're including time, those sinusoidal features, in all of our data frames. The weather, we'll look at all of them. The A versus S means, am I going to look at system-wide aggregation versus station-level data, tokenized by station? And the I versus C is whether I'm doing individual hour predictions versus cumulative predictions over a variety of hours, say like forecasting the total ridership over a 24-hour period in the future. With so many different possible things to explore in this data set, and one has to make decisions. So at this point, I've focused on this one for now to learn as much as I can about the patterns, the overall general ridership patterns that will hopefully enable me to reduce the size of the data space that we need for the station level analysis to come later. Are there any questions on what we've done before I move into data windowing?
I just had a question about so you normalized everything except for the ridership data. Is that what you said?
That's correct.
Okay. Because I mean, what I had learned was, normalize everything so that everything's on the same playing field. And you yourself pointing out that may hurt the model a little bit. So I'm just curious as to why not do that? Why not normalize the ridership? I'm just curious.
So the reason that I did not normalize the ridership yet was I was trying to trade between multiple objectives when I was working through this section here, thinking that, well, we're going to want these things to be used as counts when we're looking at station level data, and those are going to be smaller numbers on the order of between 0 and 3 per hour, in which case we're basically on the same scale already as the normalized data. For the aggregated data, I ended up making the same decision and keeping them unnormalized for that. It's something that, I could certainly revisit it. What it tends to do, of course, is it makes your training go faster in one direction than another. And so maybe you kind of take a suboptimal path to the correct minimum or to a good local optimum. I do agree that normalization is the way to go in general. And so, I'm not sure what the overall effects exactly is here, but that's what I was thinking at the time, was to just keep it in the form of integers, so to enable the station level classification later.
So for the sake of the simplicity of reading your results, kind of is
that as well, yeah, and for the simplicity of debugging all sorts of issues that arose as I proceeded through the subsequent sections. Doing integer math in my head is easy.
Yeah, that's true.
Floats is much harder.
Thanks, Robert. Appreciate it, man.
But that's a very great point, and so thank you for illustrating that a little further. Like it is somewhat of a no-no. So just wanted to describe my thoughts on it. And would be very curious to hear others' thoughts on it as well, if they've faced similar questions in data sets that they've worked with. That discussion can occur either now or on Slack, or we can move on. Let's see. Data windowing is where I'm going next. So this tutorial notebook here has this section here on data windowing, and they present remember we're back on the weather data at this point. And the idea here is that for time series models, we want to be able to access data from the past over a certain window, a certain finite sized window. You can imagine a model that uses all the data from the past, some kind of massive RNN or something. But for most of the models we'll be considering here, we'll be looking at a finite, well-defined data from the past. And they've introduced a construct and defined a window generator class that takes a handful of parameters, input width, label width, shift, and generates a few properties and other things that will be super useful for our task of building data set generator objects in TensorFlow. So as an illustration, they have created a couple of windows here. So if you give it an input width of 24, label width 1, shift 24, which index values in the original data set are we looking at? We're looking at data sets labels, so index 0 all the way up through 23. These will be your input features, and you're trying to predict the one at index 47. So it's kind of like you have one full day's worth of measurements, and you're trying to predict the measurement 24 hours later. So this shift here is always the distance between the label index, the last label index, and the last input index. So of course you can define these. Now that we've defined the function, you've got them in any way, different input width, different label width. In my notebook here, I put a number of examples here. I am going to call this function TF window generator because I ended up deciding to modify the entire class and change some things about it. So this is TF window generator to signify that it's the original one that TensorFlow provided in their tutorial. And I went through the same two examples that they did, and then I'm calling these W2T for the same reason, the T representing that it's a TensorFlow window generator class, just that it came from that tutorial, and it operates a little bit differently from the one that I ended up implementing. So you can choose to have multiple label columns. Here's an example where I chose bike and dock as output columns. This enables you to have more than one feature labeled as something that you're interested in outputting. And here's an example of a really large window where you might be looking at the entire, or this is actually bigger than my, well, no, 10,000 is smaller than the data set. 90,000 is the size of the data set in total. So just looking at a large but very general definition of windows. These will be used for indexing into the original tensors to select the correct features to be used as inputs that correspond to a given output. They have a few visualizations, I think, of this here that may be helpful. Some data sets at window 2 here. These are the data points that you need. This will be your input, that'll be your label. They also go on and show a couple of other related methods. One of them is split window, which just takes that window generator that already exists and yields inputs and labels as separate objects, your X and Y for your prediction task. And they show a plot of what some of these windows, actually just W2, looks like. So you're sampling random sequences from your data set. And in these 7 sequences, each of which contains 7 consecutive points, you're looking at, here's a value, here's 6 values, and you may be using this sequence to try to predict that one, which was the next one in the data set. And I replicated all of these functions, giving them labels tf underscore with the same thing. Changed the, I think the split window I didn't change at all, but the plot function I changed, modified a little bit. These are all just replicating their examples. I did it on a couple of the extra windows I defined to get a view of what that looks like. This one is interesting. The W8 that I had defined actually has overlapping input features and labels, which seems like it could be a leakage problem if you're going to use this for X, Y prediction. But it turns out to be a very useful window to define for visualization purposes for your model, as we'll see in a bit. Time series dataset from array. This is the tutorial function that generates a dataset, a dataset object in TensorFlow, which is kind of like a Python generator. It just yields batches of data points based on the parameters you feed it in. And this is a super useful function that they built in a more recent version of TensorFlow. For my own purposes here, I often like to develop on my laptop, so I'm not reliant on Colab notebook provisions and stuff. And my laptop, the highest version of TensorFlow that is easily compatible with my GPU is 2.1. And this function actually did not exist. But I said, okay, no problem. I'll just copy it from the source codes all available on GitHub and throw it in here myself. Ended up doing a very deep dive into how this function works and deciding that I would have designed it differently and deciding to modify it slightly for my own purposes down here. We'll go through make dataset is another option, or I'm sorry, it's a wrapper that's built around the time series dataset from array function, and basically takes your data, which is usually the data frame, a train data frame, validation data frame, test data frame, and converting it to NumPy, running it through this dataset from array, which is going to yield batches in a 3-dimensional tensor, batch size by total window size by number of features, and then just return it and split the window and return that. A couple of extra properties that they defined, copied directly from the TensorFlow code again. And I wrote this little print batch structure thing just to help me understand what was going on in these data functions. So one thing that you may notice here is that the properties train are using 3 different data frames. And I consider this to be a simplification that can be useful for certain prediction tasks and could really compromise your ability to do other ones. And let me elaborate on that a bit. For the weather prediction task that TensorFlow is doing, it is generally sufficient to consider a pretty small window around the just recent data to predict what the weather is going to be at a certain hour. Just look at the last week's worth of measurements, and that's a pretty good predictor if you're only considering predicting a few hours in advance. The problem with having these things defined as splits like this is that if you are trying to predict on the validation data frame, you're actually not using every point in the validation data frame. Not every point is being used in your label space. What you're doing is your window, you have a certain window width and then a label width, and you're only able to start including in the batches points where the entire window was part of your validation year. So as an example, suppose I want to consider a week's worth of data in my window. That's 168 points, 1 point for each hour. And what that would mean using this approach here is that my generator, the first label that it's going to yield is going to be on January 8th, because it needs a week's worth of warm up in order to find that first label point. Since I'm only using 1 year for validation, I'm starting, the validation set is all of 2018, the test set is all of 2019, and the training set is the data from before that. What I wanted was the flexibility to consider much larger windows, thinking two things. One, the data from a year or even 2 years ago could be especially relevant to this prediction task. For instance, it might help you learn the structures around holidays and when people tend to ride around particularly busy holidays, such as Independence Day, the 4th of July here in the United States. There may be very different ridership patterns on that day than on other days. And if we're not looking back far enough, we may not be able to capture that. The existence of the sinusoids representing point in the year can be helpful for this, but I wanted to see if I could generalize this a little bit further and enable myself to use the entire validation set, not just the portion that's been shortened by the window. So that's why I rewrote the function. We'll look at a couple of the original TensorFlow batches here. So just to illustrate this point, you'll see that the validation, this is the test set 2019. The size of the data set in terms of number of samples actually depends on the shape of your window. So if your window is wide, then you're going to be producing less data. Not a huge deal if it's a small portion of the year, but for that really wide window that I produced, it's just not going to come up with anything. So I won't have time to go into all the details here of exactly what I did within this window generator function, but instead of storing 3 separate data frames, I'm storing the original data frame and storing 3 slice objects in Python that indicate where in the data frame to look for the training points, the validation points, and the test points. So that now, if I want to include the performance on the first day of January in my validation set, I can use the end of the training set as my features to feed into that window. A lot of details on this. This was a large portion of the work that I've done on this notebook so far. Not sure which details here are most relevant, just replicating the same basic idea from the last part, redefining the plot function a little bit differently, defining the time series dataset from array a little bit differently than it had been defined before. Essentially, I added 2 more arguments. The label width gave it a default value of 1 if we're only going to predict one hour at a time, and the label mask, which I can feed a slice object to mask out part of the full data frame, which I'll use to select the validation set or select the test set. And that is down here. Just added a few extra lines in here to determine if the label mask was provided. Then you're going to start and end at different points in the original data frame. I also found an interesting artifact here, which I'm not sure if it's a bug in the code that I found on TensorFlow's website or if they actually intend it to work this way. But if you look at the example that they show here, time series data set from array, here we're considering an input array, indices 0 to 99, and sequence length 10, sampling rate 2, sequence stride 3. We want to yield batches with these properties here. And what do we mean by sequence length? Each sequence has 10 elements. Sampling rate means that their difference of 2 between each element. Sequence stride means that each sample yielded in the batch is 3 later than the previous one. And it turns out that the last sequence yielded here is this one. And I looked at that and I thought, well, why not yield another sequence? Because there should be one that ends at 99. And it turns out that this function over here, the original function contained that language in it. And I thought that it should have been this one. It's possible that there is a good reason for why they want to cut out the points at the end that where the stride would actually give different values depending on where you are. I haven't thought about that enough to comment on that further, but so I didn't submit a pull request or anything, but just thought it was interesting. I also don't think it's going to affect 99.9% of prediction problems that are using TensorFlow. Really won't care one way or the other. It's just something that I found while digging in very deeply into the code. So I wrote my own wrapper around this function to give additional functionality, allowing to set a few extra features in the make dataset function. This way I can make the training set shuffle while the validation and test sets do not shuffle. There's no need to shuffle the val and test sets when you're just looking at them at the ends of epochs. And for debugging purposes in later steps, this was super useful to have a method that did not shuffle those data frames. So the next portions of the notebook just demonstrate some of what I just mentioned here. Here's the TensorFlow version of time series dataset from array, generates a 27 by 10 tensor. My edit to that same function gets the last one, generates a 28 by 10, as we just described. Only matters if you're using strides and sampling, which I stopped using after this point. Then just trying to understand a little bit more about what the code is doing. Some examples here. In this case, I decided to give a label mask. So we're trying to predict on the validation set, but now we're predicting multiple points at a time, like we might be doing in an RNN with returning sequences. And in this case, we want to make sure that everything within the label mask slice, so I'm saying maybe my validation set is from 50 to 70 slice. So I want to make sure that every one of the samples I return has a point, has its 7 labels. Label width was 7, so the last 7 have to be your labels. Sequence length 10. The last 7 have to be all within the val set. So again, if you have a very large number of labels and a large number of labels relative to the size of your validation set, this could introduce some bias. I didn't worry about this. I tended to have pretty small labels in my own prediction tasks. So, and then at this point, just confirmed all the details of what I mentioned there. Any questions on Windows? Because there's pretty a lot of stuff in there. So for tonight, I'll only be describing some of the basic single-step models that we covered in the TensorFlow notebook here. I'll stop. I'll really just speed through each of these early models, and we won't get to the multi-step or the multi-outputs, which are not complete in this notebook yet anyway. So I'll just give this at a very high-level overview of what was done here. And my thought is that if we want to revisit this data set in a later deep learning day trip, where we'll get into some of the ideas that we discussed about feature engineering and other forms of modeling. We'll cover this in a little bit more detail to start then. But basically the notebook, I've followed a lot of what the TensorFlow notebook is doing. There's a baseline model which predicts based only upon the previous measurement. And you can see that visually right here using the wide window that we described earlier. It's a very nice tool for visualizing this kind of thing. But it shows exactly what it says it does. It just uses the value at time step t-1 to as your prediction for the value of time step t. You generally don't do super well with that. You get a MAE, in this case is the metric I'm using, 142 over the whole data set, and these are values that are ranging from 0 to 2000. I don't know that I have a clear visualization of that, but these are the aggregated numbers. Generalized baseline model. This was pretty interesting. So I thought, if you're going to use a single point to predict, does it have to be the one right before? Certainly in the weather data set, it makes a lot of sense to do that. For the Bikeshare data set, maybe it doesn't. Maybe the point that's exactly 24 hours before is a better predictor. Maybe the point that's exactly a week before is a better predictor. So I did a number of tests on that. Eventually came down, calculated the baseline model for a variety of possible offsets, and you get an interesting little viz of the seasonality effects. So what's going on in this figure? Here we're looking at possible hourly shifts over the course of a couple weeks. This is about 2 point some weeks worth of data. And each one of these red points is an integer number of days. So you're returning to the same time of day. That should be a better predictor, and it is. The 1 hour MAE is down here. So 1 hour looks like it does a little bit better than 24 hours, but it turns out that 168 hours is a better predictor than either of them. So the weekly effect does manage to overcome the proximity of days here. And you could continue this for larger time shifts as well. And in fact, I did that and generated this other figure here where I'm looking at over the course of a couple of years now, only considering the shifts that are integer days. And now the red points are shifted by 364 days. And that turns out to be the best baseline predictor over the course of years. It actually turns out to be even better than the 1 week predictor, which I thought was interesting. The 1 day predictor here does have the advantage of high correlation in weather, not just climate, but weather. Once you go out here, you certainly get some climate correlation, less weather correlation. But when you look at the entire data set, it actually turns out to be quite helpful for the baseline model to look at back 1 year. 2 years does pretty well too. So I thought that was interesting, and also informs the choice of how do you really want to model these things going forward. The TensorFlow notebook then shows a variety of models: linear, dense, multi-step dense, convolutional net, recurrent net. I didn't change much of any of what was done in the TensorFlow notebook for some of these until we get into the Lstm. Here we're just looking at, they define a pretty useful compile and fit function, which is just a wrapper, automatically chooses a patience of 2 with early stopping, monitoring validation loss. One thing we will see here is that this early stopping is not generated over 20 epochs in many of the examples. I think this is possibly an indication of the choice of not normalizing the ridership aggregate numbers. But that could be looked into further. Just wanted to get something down. you'll see that this one I printed out, the whole sequence, it's dropping somewhat steadily and hadn't yet converged after 20 epochs. But you do see that it does significantly better. The linear one-step model gets it down to MAE of 99. Then we'll consider a dense, which is really just a linear model now with a not a linear model, but a multi-layer neural network model, nonlinear. And that does somewhat better, significantly better actually, a mean absolute error of 59. Not surprising that a lot of the effects we're looking at in the data set, a linear model won't do too well. Multi-step dense is sort of a stepping stone to the convolutional model that they present. I didn't change anything in here from the tutorial. Not much anyway, just a little bit of, I think just looking at the input shape here, just to understand what exactly is happening at every step. Convolutional net allows one to fix the fact that the dense models are expecting a fixed window size. ConvNet allows you to define a model before you've actually entered an input shape, so you can define a model more generally, where running the summary will give you an error. But then, of course, you can clarify that to the model. It'll build it right here when you first try to call it on an example window. It'll just infer what input shape you wanted, then it'll build it and give you a summary. Couple different convolution windows. Predictions are starting to look somewhat better. And what was the MAE on that one? Well, this one's back up to 70. I think we didn't plot the one for multi-step dense. The Lstm I did want to say a few words about. They are running a sequence of 24 outputs, which is, they're using the return sequences equals true option, which basically forces the Lstm to output something at every step. I think there may be a decent visualization of it down here. Right. So if return sequences is false, you would get you'd feed it 24 hours worth of data and you'd only get one output. For return sequences equals true, you feed it 24 hours worth of data and you get 24 outputs. So what's interesting about this is that now you're training on all of these things. Not only are you outputting these things, but you're trying to optimize a loss function that is related to these things as well. So first of all, I trained it with return sequences false, only looking at one output. Inspecting the model, just making sure I understand what the model is doing, looking at the shapes of each layer, all made sense based on the definition of the Lstm and the values that I had put in. Then, let's see, looking at the mean absolute error of this model compared to some of the other ones, the Lstm was actually not doing as well as the multi-step dense or the dense model. And interesting that it was different between val and test, but still wanted to, these numbers are test, val was up over 60. Still wanted to know what was going on. So started looking at return sequences equals true and generated a new set of windows for that. Did a number of analyses here on the residuals of the possible predictions. So what's interesting about using this model here is that you might be able to make a really good prediction down here by the time you've seen 24 hours worth of data, but you've only seen 1 hour worth of recent data here, so you can't be expected to make as strong of predictions. The evaluate function, which is used to train TensorFlow, actually uses all of these, and it seems to treat them equally as far as I can tell. So my hypothesis here was that if we're trying to optimize at time step 1, we may be compromising our ability to optimize down here. So I was expecting, well, we're not going to get as good a results by looking at this full array, right? We'll see predictions that have, I think I passed by it. No, maybe it's down. Yeah. So we'll see a residuals pattern that looks a little bit like this, where we have good numbers down here, 56 for the further out time steps, but the early ones were doing quite poorly, and the overall reported number is an average of those. Although it seems to be not exactly an average, so I didn't quite figure out why those were not exact, but it seemed to track it quite closely. So I wanted to compare it against the single output sequence. No, I guess that one was return sequences equals true. Sorry, I misspoke. That one was return sequences equals true. And my thought was, well, I'll do better if I'm only looking at the last one, because I'm not biasing my LSTM parameters and the weights within my cell state and the other hidden units by trying to optimize at these early stages. So did a bit of work on this one. It's the exact same model, except the outputs are just removed. So it actually has the exact same number of trainable parameters. It's just not outputting anything in the intermediate steps. So, and actually my hypothesis was completely wrong. It turns out that the mean absolute error was much worse when I got rid of the early parts of the sequence there. And I thought, what could have caused that? And did a little bit of thinking about it, and what I believe is actually happening here is by cutting down the number of outputs by a factor of 24, it's almost like you're reducing the size of the data set. By you're only training one training example per point. You're saying, I want to predict this point, and I'm giving you 24 hours of data to predict it. Using return sequences equals true, it's like, well, I'm going to predict this point using 24 hours worth of data, but I'm going to have a different training example where I'm using 23 hours worth of data trying to predict that same point, a different example where I'm using 22 hours, and all the way down to 1 and 2 hours. And so it's almost like you're doing some kind of data augmentation where each predicted value, each labeled value, you're trying to predict it 24 times with slightly different models, slightly different numbers of steps having been fed to the model, slightly different amount of time for the cell state to adjust to the observations. So I thought that was really interesting. I do think that it may actually reverse if we were to train everything out to the point at which the validation set starts turning around. I mean, right now we're still dropping in validation MAE as well as training. I didn't go into that, but I did think that was interesting. And then I looked at maybe a useful middle ground. What if we only predict the last 18 outputs, because those ones looked really stable, all outputting the same value, while sort of a trade-off between getting the benefits of this augmentation while not biasing the model so much by trying to predict on unwarmed up cell states. And this one actually did not do as well as the 24-hour prediction. So my thought here is that it's just simply, in spite of the fact that your overall MAE looks worse when you include these points, it's still useful to train on them to improve your predictions for the later points. You're still apparently learning something useful there. and improving the speed at which you're training. So it's obviously after 9 o'clock, and I think now is, if we don't stop now, we might not be able to stop. So, and this is a good point because this is the point of the notebook at which I'm still working through a lot of the details beyond here on the multi-output models. So I've been speaking a lot the last hour or so. Are there any questions before we wrap up for this evening?
Robert, I don't know if Ted's still here, but he was wondering if you recommended a good book on time series prediction. If you had
A
any
good book on time series prediction. So I do, and I'll respond to him on Slack, I guess, if
Sure.
he's not still here.
I'm still here, Robert.
Oh, okay. Never mind then. So I do not know of a book that does time series specifically for neural networks and Python, but I have found the text through Springer by Brockwell to be super useful for more of the traditional time series work. There's a really great exposition there of autoregressive models and a lot of the theory behind time series. I think I seem to recall having this discussion with someone on Slack a month or two ago where I may have recommended that same resource.
You
Okay, cool. Thanks. I'll definitely check it out.
But it's just as a word of caution, it's a more of a how to do it in R book with a lot of theory behind it as well. So if you're not an R user or intent on becoming one, it may have less utility than the author originally intended.
Okay. Yeah, I mean, for me, it's a weakness just in terms of a lot of the theory. So it sounds like it'd be a good book for me, and since I do know R, that shouldn't be a problem.
Yeah, I found it pretty good. There are some other ones. I think there are other ones, but they don't just focus on time series. Whereas I think the Brockwell book is entirely time series.
when you're talking about like traditional well, algorithms, I suppose, are you talking like Ceramax? That's the auto regressor one, right?
This is the book here, by the way. I think there's a later edition of it. I'm sorry, I missed your question, Ozire.
I was just the algorithm that you're the traditional auto regressor one algorithm you were mentioning, that is Ceramax, I think it's called Ceramax.
Yeah. So Ceramax is one of a family of models that are based on autoregression and are usually applied with linear models. But you can start with a very simple, the Ceramax is, for those not familiar, it's an acronym, which is seasonal, auto-regressive, integrated, moving, average. I don't know what the X is, something.
I think it's not
and it's really just an indication of how many different components all go into the Ceramax model. There's seasonality, there's auto-regression, which is like using recent measurements to build a linear model to predict current measurements. Integration allows you to deal with drifts by, the term integration is for assuming that the data set was integrated. What you do is you difference the data set to try to come up with a stationary time series. Then you also have moving average models, which are a different flavor of using recent data to predict the current timestamp. But yeah, all of those are described in this book in detail.
Yeah, thanks, Robert.
Certainly. If it hasn't already been advertised, the notebook that we just went through is available on my GitHub. O2 models here. You won't be able to run it without my database where it's reading from to start. If you are interested in pursuing some of this yourself, and maybe doing a related analysis like Kathleen was gracious to share with us this evening, please let me know. I'm happy to share what I have. Just not putting the data set up here. And I will also note that the weather information I collected was through a paid API. So I may not be, that may not be something that I would share. I think the terms may prohibit that. However, it's a very cheap data acquisition because you're only looking to acquire weather for one city. I think the data set that I used cost like $9 or something.
All right. Any other questions for Kathleen or Robert? Nothing heard. I will continue on. I want to thank both Kathleen and Robert for these excellent presentations. Incredibly interesting, and we may have to explore this further. I feel we might have another.
As I said, I'm just scratching the surface here. I could certainly have. I wish we had taken a little bit. I wish I had saved a little bit more time for sections 5 and 6 there in the notebook, because there's a lot of details that we like to dive into the details here at DLA. And a lot of details that I really glossed over. But I do want to continue to pursue, extend these models to station level predictions and user level predictions, and take into account some of the features that might be engineered from elsewhere, learn representations of the stations. There's a lot of ways that one could take this further.
I think you may need a few more months before you're ready to present it, I suspect.
Well, I think we have plenty of other topics that we can cover in the next couple months, so
right,
not a problem.
So speaking of that, let me share the screen here. Next, I hope you can see my screen now. Next week, we're going to be diving into a new Kaggle course they put out. We wanted to cover this one. We thought it was really important. There's been a lot of discussion, particularly in the last few months, about AI and ethics. And they introduced a new course of Kaggle that we're going to go through. It's got a basic introduction chapter, talks about human-centered design for AI, and then bias, which is a really important topic that we're hearing a lot about, fairness in AI, and then ways that you can be very transparent about your model and the data and the training that went into it. So looks like a very fascinating course, and we're going to try to tackle this next Wednesday. I think George is going to post the announcement on the meetup page today or tomorrow, if not already. So please join us next Wednesday. And that's all I have for tonight. I'm going to go ahead and turn off the recording.